In this video, let us learn about Maintain Controls. Maintain Controls, Section Overview and Objectives. By the end of this lesson, you will learn to describe measurement system reanalysis, explain control plan, measurement system reanalysis, maintain controls, measurement system reanalysis. Process improvements often result in reduced variation. With an increased understanding of a process, variation that previously was considered to be random or chance-caused variation can be reduced. Continuous improvement efforts resulting in reduced process variation may require a re-evaluation of the measurement systems. For example, micrometers that measured to 0.001 inch were used for several years. As machining capability improved and as the specification requirements became tighter, micrometers with the ability to measure to 0.0001 inch became necessary. Although both of these micrometers still have many applications today, more accurate instruments, such as super micrometers, are now required for some length measurements. Using specialized equipment in temperature and humidity controlled rooms, measurements to 1 millionth or 0.1 millionth of an inch for length are possible today and are routinely done. An old rule of thumb was that the measurement instrument needed an accuracy of 1/10 that of the specification tolerance. This was also stated as the 10-to-1 inch rule. If the specification required 0.345 inch plus 0.005 inch, 0.345 inch plus minus 0.005 inch, the proper instrument had an accuracy of 0.0001 inch. Because the specification required measurement to the nearest 0.001 inch. Some interpreted the requirement as 0.0005 or 0.001 based on the 0.1 of the tolerance. Other sources used a 4-to-1 ratio or the equivalent 25% as a guide for the measurement uncertainty as compared with the specification tolerance. The disadvantage of either of these rules is that in some applications achieving a 10-to-1 ratio is easily done, while in other applications it would require expensive equipment to attain the suggested uncertainty. Maintain controls, measurement system reanalysis. The new quality system standards require an estimation of the measurement uncertainty as well as statistical techniques for analysis of test and/or calibration data. Actually, this is not a new requirement because similar wording was in MIL STD 45662A 1988. The collective uncertainty of the measurement standards shall not exceed 25% of the acceptable tolerance for each characteristic being calibrated. For automotive suppliers, Quality System Requirements Q3 9000 1998 states, appropriate statistical studies shall be conducted to analyze the variation present in the results of each type of measuring and test equipment system. The analytical methods and acceptance criteria used should conform to those in the Measurement Systems Analysis Reference Manual, for example bias, linearity, stability, repeatability, and reproducibility studies. The guidelines for acceptance of gauge repeatability and reproducibility %R&R are less than 10% error. The measurement system is acceptable. 10% to 30% error may be acceptable based upon importance of application, cost of gauge, cost of repairs, etc. 30% error. Measurement system needs improvement. Make every effort to identify the problems and have them corrected. Note: although the factors are different, the term less than 10% looks similar to the 10:1 ratio, and 10% to 30% looks similar to the 4:1 ratio or 25% from earlier methods. The expression of measurement uncertainty includes both the range and the level of confidence at which the statement is made. Each organization needs to determine the measurement system requirements and evaluate if the measurement system capability meets those requirements. The requirements are dependent upon customer specifications, the intended use, and costs of implementation. As the process capability improves, the measurement system needs to be re-evaluated to determine if requirements or measurement capability also needs to be improved to achieve the desired levels of control. Control plan. Maintain controls. Control plan. A control plan is a document describing the critical to quality characteristics, the critical X's or Y's of the part or process. Through this system of monitoring and control, customer requirements will be met and the product or process variation will be reduced. However, the control plan should not be a replacement for detailed operator instructions in the form of work instructions or standard operating procedures. Each part or process must have a control plan. A group of common parts using a common process can be covered by a single control plan. Types of control plans. For the automotive sector, ISO/TS 16949/2002 and the Advanced Product Quality Planning APQP 2000 identify 3 control plan phases: prototype, pre-launch, production. A prototype control plan is used in the early development stages when the part or process is being defined or configured. This control plan will list the controls for the necessary dimensional measurements, types of materials, and required performance tests. A pre-launch control plan is used after the prototype phase is completed and before full production is approved. It lists the controls for the necessary dimensional measurements, types of materials, and performance tests. This plan will have more frequent inspections, more in-process and final checkpoints, some statistical data collection and analysis, and more audits. This stage will be discontinued once the pre-launch part or process has been validated and approved for production. A production control plan is used for the full production of a part. It contains all of the line items for a full control plan. Part or product characteristics, process controls, tests, measurement system analysis, and reaction plans. A more detailed list of input factors is provided later in this section. Maintain controls. Control plan organization. The control phase is the forgotten C in DMAIC. The project control phase is necessary in order to sustain the project gains. The control plan must be a living document for it to remain an effective mechanism to monitor and control the process. A responsible person must be placed in charge of the control plan. This ensures successful monitoring and updating. A black belt may or may not be a suitable person for the role, as he/she may be replaced or transferred to a different position. A better selection would be the process owner. The current process owner can be listed on the control plan, but in reality it is a functional role that is to be passed on to the next individual in that same organizational position. If the control plan is not maintained, the benefits of the project could slowly be lost. The frequent changing of process owners, combined with large numbers of process projects, can easily result in neglected or lost control plans. Some considerations in the closing phase of the project include: identify the process owner, involve the team in the control plan, create new or updated work instructions and procedures, notify and train the affected personnel, ensure that the control plan training is effective, place the control plan in the proper quality system document, attain agreement between the team members and process owner, maintain controls, control plan input sources. A number of inputs or sources contribute to understanding, manufacturing, and controlling the part or process. Many of the following are included: process flow diagrams, system FMEAs, DFMEAs, and PFMEAs, cause and effect analysis, special customer characteristics, historical data, lessons learned, team process knowledge, design reviews, quality function deployment, designed experiments, statistical applications, multivariate studies, regression analysis. Customer requirements may dictate the exact form of the control plan. Often, there is some flexibility in the construction of the forms. Maintain controls, description of control plan line items. Control plan. Provide a title for the control plan. The control plan will often be placed into another document, such as an operating instruction or Six Sigma database. If necessary, indicate if this is a prototype, pre-launch, or production plan. Control number. Provide a reference number. This number may be supplied by the responsible department. Team members. If a cross-functional team is involved, provide the members' names. Contact person. This could be the black belt in charge of the project. However, the name and function of the process owner are more important. Page. Provide page numbers if the control plan exceeds 1 page. The examples shown in this description are brief. Control plans may run up to 20 pages. Original date. Indicate the original date of issue of the control plan. Revision date. Provide the latest revision date of the control plan. Part process. List the part number or the process flow being charted. Key input variable X. Note the key input variable when appropriate. On any line item, only the X or Y variable is filled out, not both. This is to clearly indicate which item is being monitored and controlled. Key output variable Y. Note the key output variable when appropriate. Special characteristic note. Indicate if a special characteristic is to be monitored and controlled. Specifications. For manufacturing applications, the engineering specifications for the part should be monitored and controlled. For other applications, one would provide upper and lower specification limits as well as the target value. Measurement gauge technique. The gauge or measurement technique should be described. The gauge, tool, fixture, or test device used for data collection must be in conformance with the needed measurement system analysis (MSA) requirements. When necessary, this would include linearity, stability, accuracy, reproducibility, repeatability, and uncertainty analysis. This can be more difficult when attribute data is of concern. The AIAG MSA manual is a good guide. Gauge capability. Provide the current capability of the measurement system. The AIAG MSA manual lists under 10% error as acceptable. 10% to 30% error may be acceptable depending on the cost and the situation. Over 30% error is not acceptable. Measurement devices may need uncertainty determinations. Sample size. Provide the sample frequency. List how often the inspection or monitoring of the part or process is required. Initial CPR. This provides an indication of process capability. Person responsible for measurement. Indicate who will make and record the measurement. Control method. Note how this X or Y variable will be controlled. Examples include control charts, checklists, visual inspections, automated measurements, etc. Reaction plan. Describe what will happen if the variable goes out of control. How should the responsible person respond to the situation? Control plan construction is often led by the black belt in charge of the Six Sigma project. The team is usually cross-functional with individuals from different areas, including the process owner. The team will ensure that the control plan contains the critical variables, the X's and the Y's, of the product or process. The control plan must show compliance and control before project closure. A successful control plan will remain a living document to ensure that the benefits of the project will be fully realized. Summary. Maintain controls. In this session, you learned about the following: measurement system reanalysis, control plan. Now you should be able to understand measurement system reanalysis and control plan.